Hello, this is Andrew Coe, and this is a video analysis of my breaststroke and coupling involved in it and the physics involved with it. So let's just play this through first. So this is CIF's final, and that's me in the middle leading the race. It's 100 breaststroke. Okay, so let's analyze. So right here, breaststroke is the stroke where you do a dolphin kick and a pull out, and I do the dolphin kick pull out and I break surface tension, break the surface. Takes quite a bit of energy, as explained before in the presentation. Surface tension takes a lot of energy to break, and obviously you can see that I'm doing that because I'm pulling on the water. Like these little lines are my arms, and I'm pulling. I'm applying force and work to bring myself out of the water from the surface, and I throw my head down, and then I time myself throwing my head down with a kick. That is coupling motion. Coupling motion is when you combine two axes in movement to interact with each other, and when you swim, it helps increase the velocity or momentum in the water. So why do I do this coupling motion? So if I was to be hooked onto a velocity meter, the graph of my velocity would look something like this. Something like that. So this right here is when I kick. So breaststroke is a kick-based stroke. Kick has a lot of power, and you are in your propulsion phase when you finish your kick. And this is your pull. And the reason why there's these troughs of essentially no velocity, zero velocity, is because breaststroke is the only stroke out of the other three strokes that there's a point in time while you're swimming where your velocity is near zero. So if you pay attention to, I'm not trying to criticize anyone's swimming, but this kid right here, if you notice his stroke, his head barely comes out of the water. Let me play it in full speed. Barely comes out of water, and I don't know if you noticed, but you can clearly tell that there's like a little pause. Boom, 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 pause. There's pauses in his stroke, and that's where the zero velocity occurs. So why is there no velocity occurring in the stroke? Oops. So in swimming, there's a body line vortex. So say this is your body, you're swimming. This little two lines, they represent your body line vortex, and that's how the water passes over you. And if the water passes over you smoothly, that's laminar flow, the least amount of resistance. If for some reason, well, there is always a reason, but if somehow any body part sticks out of the body vortex line, this will cause turbulent flow and lots of resistance and lots of drag. And obviously drag is not going to help you because it will slow you down a lot. So how is breaststroke related to this? Well, breaststroke, going back to the vortex line, body vortex line, will give me an example, my body vortex line. So I'm high up into the water, and okay, this is a very bad drawing of me, but this is my neck. Okay, looks very weird, but this is my knees, and I get up this high by contracting my back muscles along with the pull. So I'm basically pulling while also contracting my back muscles to bring myself at around a, well, first off, almost 90 degrees, and then later on, once again, very close to 90. Not exactly 90, but very close. So anyways, so that's me. That's like a little drawing of me in the water, side view with the body vortex. So this is breaststroke. You can see that the knees clearly exit the body vortex line, your body line, as some swimmers would call it. And if we go back to this kid with the mediocre stroke, to say the least, his head is barely out of the water, obviously because he's not contracting his back muscles and not using his arms to propel himself out of the water. His legs are probably like this. He's probably like in the water like this. So obviously, which is better? Knees barely like this. Knees barely like this. In line, only this amount, or this huge amount. Your entire leg is out of line. So yeah, that's what he looks like underwater. Like, I promise, that's what he looks like underwater. And that's why in breaststroke, if your technique is not the best, you'll experience this little pause. Let me try to, right here, right when he's bringing his head back down, he's almost at a standstill. I don't know if I can slow this down. I can't, but he's essentially at a standstill. Yeah. So that is why you throw your head down. That's why you throw your head down while swimming breaststroke, because your head is like around 12 pounds of mass, and throwing that down is going to generate momentum. And if you have momentum while if you have you can carry this momentum into the kick, which causes a lot of drag. So you carry that momentum into the kick, which lessens the amount of frontal drag and it increases the propulsive force. So you do experience a very slight dip in velocity, but you still experience velocity, so you're never stopping, essentially. So yeah, that's my little video of my breaststroke and coupling motions.